What lies beyond the farthest edge of the universe? Not just beyond the stars or the galaxies or even the cosmic microwave background, but past the very limits of time, space, and understanding itself. Scientists have mapped the observable universe to astonishing precision. Yet beyond the cosmic horizon is a realm untouched by light, unreachable by telescopes, and unexplained by our best theories. Is there more universe out there or something entirely different? In this deep dive documentary, we'll journey to the limits of known science and step into the unknown, exploring every wild possibility, parallel realities, multiverse bubbles, cosmic mirrors, and the haunting silence of true nothingness. The observable versus the entire universe.
The universe that we can see is about 93 billion light-years across. That's because the universe has been growing since the Big Bang. The space between galaxies has grown a lot in the 13.8 billion years that the universe has been around. Light from the farthest reaches has just barely made it to us, leaving us with a limit that we can't see past. We can't change this because of our technology or our lack of knowledge. It's just how reality works. Since the beginning of time, no matter how good your camera is, you can't see past the speed of light.
And here's the twist. Beyond that edge, the universe may go on forever. Picture yourself floating at night in a huge ocean. In the distance, you can see a ring of sparkling city lights. This is the only sign of society you can see. You don't know how far the towns go out into the distance, or if that's even where the world stops. That ring of light is like the universe we can see. It's just a small part of it, because light has to travel a long way to get to us. There could be more stars, galaxies, science, and maybe even things we've never even thought of beyond it. So how do we define the entire universe? That's a question that borders on the philosophical as much as the scientific. The observable universe is what we can study, but the full universe is what is, and the gap between the two might be staggeringly large. A lot of people agree with inflationary theory, which adds to the Big Bang model and says that the universe grew very quickly in the first few fractions of a second after it was created. It was during this increase that quantum fluctuations were spread out over very large areas, setting the stage for the large-scale structure we see today. But inflation doesn't always stop all at once, and in many models, it never does. Eternal inflation is the name for this, and it makes people think that the universe may only be one pocket in an endless number of them. If inflation did continue beyond our cosmic horizon, then there could be a near-infinite expanse of universe out there, identical to ours in some places, bizarrely different in others. Galaxies might form under the same laws of gravity and thermodynamics, or maybe other regions have different values for the fundamental constants of nature, making life, matter, or even atoms impossible. And we would never know, because no information can reach us from those places. The fact that we can't connect with most of the universe is built into the very nature of physics. The speed of light is not just a guess, it is the fastest thing that can ever be. There is no way to go faster. In other words, the world may be endless, but our understanding will always be limited to what we can see. Some cosmologists use the form and curve of space to try to guess how big the whole universe is. So far, all measures point to space being flat. If that's the case, it could go on forever, but it's possible that the universe has a limit. Even if space is flat, it could wrap around itself in strange and interesting ways. In theory, you could go in a straight line for billions of years and never come across an edge. You would always end up back where you started. That said, when we observe the cosmic microwave background, the oldest light in the universe, frozen just 80,000 years after the Big Bang, we see patterns that seem to suggest uniformity beyond the observable edge. There's no obvious boundary, no sign of a wall, no abrupt end to the stars, just more of the same, as far as the eye and light can see. But there's more than just a technical difference between observable and entire. It changes everything about our place in the universe. If the world is endless, then the area we can see is just a small part of an infinite unknown picture. It's possible that one day we'll be able to plan out the whole thing, or we might see strange signs coming from across the curve of space. No matter what though, the sky we see now is not the end. It's the most light has given us so far, and even that is slowly changing. Every second, light from further and further away is reaching us. The observable universe is growing, but ironically, the galaxies beyond our reach are also accelerating away due to dark energy. Some galaxies we can see now will eventually become unreachable forever, their light stretched into invisibility. The edge, in a sense, is both advancing and receding, a cosmic tide we can never quite catch. When someone says the edge of the universe, know that it's not a wall, a cliff, or the end. It's a line that's drawn in time, not place, a limit set by light speed, and the fact that space is always getting bigger, and beyond that, maybe more galaxies, maybe another universe, maybe the end of physics as we know it. The horizon of time. When we talk about the edge of the world, we usually think of a faraway border or a line, that there is something beyond. Need more room? A wall? Nothing? Cosmology today, on the other hand, turns this thought on its head. Space is not where the real edge of our universe ends, it's on time. To understand this, picture the universe as a bubble that is getting bigger. You're a tiny dot on the top of the balloon, and as it gets bigger, other dots get farther away from you. Now for the important part. That balloon's surface doesn't have any edges, only where you can see ends up being the edge of its surface. And that edge is not based on distance, but on time. This limit is called the cosmic horizon, and it's set by the age of the universe. Light takes time to travel, so when we look deep into the universe, we are looking into the past. The furthest light we can see comes from about 13.8 billion years ago, the moment of the Big Bang, but because space has expanded since then, that light now comes from regions roughly 46 billion light-years away. This mismatch between time and distance is a key feature of cosmological expansion. So when we ask what exists outside the observable universe, what we're really asking is what exists beyond the reach of light that has had enough time to reach us since the Big Bang. The edge is therefore not a spatial edge, it's a temporal one. Imagine lighting a candle in a vast dark cave. At first, the light reveals only the area nearby. As time passes, the glow spreads, illuminating more and more. The edges of the light are not the edge of the cave. They are the limit of how far the light has traveled in time. Likewise, our instruments can only detect as far as photons have had time to journey through the universe's expanding fabric. This idea is called the particle horizon, and it shows how far particles could have moved to reach a viewer in the early universe. But there's another one that might be even stranger, the event horizon. The particle horizon tells us how far we can see. The event horizon, on the other hand, tells us how far we can ever see, even in the infinite future. These things happen because dark energy is speeding up the spread of the universe. We can see some galaxies today, but they're moving away from us faster than the speed of light, because space is expanding. It's not that the galaxies are moving quickly through space, but that space is expanding. Their light will never reach us again. One day, they will be out of our reach forever. This means there is a cosmic cutoff, not just in what we can observe, but in what we ever will be able to observe. The universe, in a real and measurable sense, is retreating from us. But this horizon of time does more than just limit our vision. It defines the boundary of our knowledge, our models, and even our capacity for meaning. Beyond this temporal veil, there may be entire civilizations, galaxies, or even physics that we will never know about. Not because we're too primitive, but because the structure of reality itself prohibits it. And yet, the horizon of time is not fixed. It's dynamic. With each passing second, more photons arrive, a deeper look into the past. New discoveries are made possible with each moment. When the James Webb Space Telescope peered further than any previous instrument, it was stretching our temporal horizon, catching light from just a few 100 million years after the Big Bang. In doing so, it deepened our understanding, not just of the universe's scale, but of our place in time within it. There is also a metaphysical component to this. The time horizon is like a psychological boundary, and not just in a cosmic sense, it's also a boundary in how we think about life itself. The idea that some parts of the world will always be out of reach, unseen, and unknown, makes us wonder what it means to live. If there are galaxies whose light will never reach us, Do those galaxies really exist in our universe, or are they two different realities? Then there's the problem of simultaneity, or how to define now when people are very far away from each other. Time and space are not absolute in relativity. There are times when two events happen at the same time, but not in other frames of reference. When you look at it on a cosmic level, this is more than just a thought experiment. It limits how we can describe the present moment in a world where motion and gravity make clocks tick at different speeds. When we look at a galaxy 10 billion light-years away, we're seeing it as it was 10 billion years ago. But what is it doing now? That question is meaningless in relativistic terms unless we define a frame, and in cosmology, that's not easy. Our now is local. Every region of space carries its own version of the present. So even if we could break through the horizon of time, we'd be reaching into something else's past or future, not our shared now. Time, in this sense, is the ultimate boundary, not space. This realization changes how we conceptualize the universe's edge. There is no wall, no fence, no limit we could travel toward and eventually reach. Instead, there is a vast and ever-growing silence, a boundary defined not by distance, but by delay. And that delay is infinite. For some things, their light will simply never arrive. But this is also beautiful, because time is what lets us see the universe. Everything would fall into a single moment. If there were no weight, no limit, no distance, it would be flat and lifeless. The universe instead unfolds slowly, like a story told through light, with each photon bringing a thread of the story through the ages. Is the universe finite or infinite? Is the world limited or boundless? This is one of the most difficult questions we can't yet answer. To even begin to answer that, we must first separate the ideas of what we can see from what might really exist. It's a sphere about 93 billion light-years across. That is the part of the universe we can see. In no way does that mean the universe is 93 billion years old. Even though the universe is only about 13.8 billion years old, space has been growing the whole time. The light from the farthest galaxies has been moving for 13.8 billion years. But those galaxies are now about 46 billion light-years away from us. Because of the expansion, that's the size of our observable bubble. But what lies beyond? There are three main possibilities, each more mind-bending than the last. The universe is finite but unbounded. It's hard to understand this idea. Consider the Earth's surface. You will never fall off an edge. If you walk in any direction, it's true that Earth has a limited surface area, but it also has no edges or borders. If you have enough supplies, you could walk on forever and never hit a wall. Now, take that two-dimensional analogy and expand it into 3 dimensions. In this model, the universe might be like a 3D version of the surface of a sphere. It's finite, yet it curves back on itself. If you could travel in a straight line long enough faster than the universe is expanding, you might eventually return to your starting point, just as a person walking around Earth ends up back where they began. This type of universe would have positive curvature, similar to the geometry of a sphere. But here's the catch. There's no visual curve in the way your eyes might detect, because space itself curves and you're moving through it. Every step feels straight. It's the universe that's looping, not your path. 2. The universe is truly infinite. Many cosmologists agree with this view. Space goes on and on. In this form, there is no limit, edge, or return path. Nothing but an endless universe stretching out in all directions, full of galaxies, dark matter, radiation, and maybe even physics we can't yet imagine. If the universe is endless, it means a lot of amazing things. For example, there might be another version of you out there. In fact, there could be an infinite number of you. Since there's only so much matter and only so many ways to arrange it, every possible arrangement must eventually happen again, just like rolling dice enough times. This is called the cosmic doppelganger hypothesis. It's not science fiction. It's a possible result of an infinite universe. Our visible universe is just a drop in an endless ocean. It's a tiny patch of sky in a vast field of galaxies that has no end and no way to know it does. How do we test for infinity? The truth is, we can't. Not directly. We can only see what we can see. That's why we use math. 3. The universe is flat, and that might mean infinite. We can figure out how big the universe is by looking at its shape, using geometry. Observations of the cosmic microwave background, CMB, especially from the WM map and Planck probes, suggest that the universe is almost completely flat. Flat geometry is what you'd expect in an infinite space. Draw a triangle on paper. The angles add up to 180 darjan. That's flat. Do it on a sphere. The angles add up to more than 180 darjan. Positive curvature. Do it on a saddle-shaped surface. The angles add up to less negative curvature. The fact that our universe appears flat suggests either that it is infinite or so large that any curvature is beyond our ability to detect, like standing on a beach and trying to prove the Earth is round with your own eyes. This flatness also connects to the idea of cosmic inflation. The universe grew extremely fast in the first fractions of a second after the Big Bang. Just like blowing up a balloon makes a small patch seem flatter, inflation smoothed out any curvature. So even if the world is curved on much larger scales, it looks flat to us. Now, here's where things get really weird. There is no such thing as an outside. Even if the world is finite, you can't point to a wall or edge. A finite world doesn't need a cosmic fence, just like the top of a balloon doesn't have an edge. If a hypersphere curves through higher dimensions, space could be closing in on itself. You'd never reach the end, because there is none. Your journey would just keep cycling through space-time. This brings us to an important philosophical shift. The universe isn't expanding into anything, it's expanding within itself. Space is being added between objects, not at the outer rim. In fact, asking what's outside the universe might be a meaningless question, like asking what's north of the North Pole. In general relativity, space and time are the fabric of the universe. Without them, there is no framework in which outside can even exist. Implications of a finite versus infinite universe. Whether the universe is finite or infinite changes how we think about everything, from the ultimate fate of the cosmos to how we define meaning. If there are limits, we might be part of a closed loop or cosmic island with boundaries defined by physics. There might only be one Earth, one you. But if the universe is endless, the story gets weirder. There may be more than one version of you, more than one account of events. Every possibility may come true, somewhere in a faraway part of the multiverse. What the universe is growing into is not just a question of cosmology, it's also a question of the boundaries of what we can think. The universe has no center. When you're floating in space, there are so many galaxies around you that it can get dark. You might wonder where the center of everything is. Where did the Big Bang take place? From where does everything grow? The truth, though, is that the world does not have a center. It didn't go off in space like a bomb from one spot. It wasn't a blast from the outside into space. The Big Bang did not happen in a certain place. It took place everywhere, because that's when space was born. Assume a sheet of rubber that goes on forever and stretches in every direction. There are points on that sheet that move away from each other. As it gets longer, everything on the sheet looks like it's getting bigger around you, no matter where you stand. But there isn't a special place. There's no center, just add more rubber. That's the way our world works. We can see galaxies moving away from each other in all directions. When we look out into space, they're going away faster the farther away they are. This is Hubble's law, and it's true everywhere. You would see the same thing from a galaxy 10 billion light years away. Galaxies moving away from you in every direction. It would make you feel like you were in the middle, but that illusion is everywhere, because the universe isn't expanding from a place, it's expanding between places. This is one of the most profound and difficult ideas in cosmology, because it defies everything our intuition tells us. We're used to objects having centers. Our planet does, our galaxy does. Even a hurricane spirals around a central eye. But the universe, it has no edge, no outside, and no middle. The universe is homogeneous, the same everywhere on large scales, and isotropic, the same in every direction. These two principles, known as the cosmological principle, are fundamental to our best models of the cosmos, and yet it feels wrong. How can everything be expanding if there's no origin point? How can there be motion without a center? So, let's use the balloon again, but be careful. If you blow up a balloon, and draw little dots on it. The dots will move away from each other. They are not all in the middle. While the center of the growth is inside the balloon, the top of the balloon is like our three-dimensional space, which is made up of 2 dimensions. That means the center isn't on the outside. It doesn't exist in the world of the comparison. In the same way, the heart of our world is not in space at all. It's not anywhere. Or maybe I should say that it's everywhere. When we say everywhere, the Big Bang did not mean that there was an explosion that sent mass into space. In other words, space was smaller, hotter, and denser, and then it grew bigger. It grew, and so did the locations we used to talk about it. There was no place to grow outside. There is no set point to move away from. In this way, the universe is like a fabric without seams or threads pointing to a middle. And if that's not strange enough, consider this. Even if the universe is finite, like the surface of a sphere, it can still have no center. Think about being on Earth. You can walk in a straight line forever without falling off or hitting a wall. Earth is a finite sphere, but it has no edge, and no point on the surface is the center of that surface. It's just curved in a way that loops back on itself. If our 3D world has a similar shape, like a sphere with 3 spheres inside it, then it might be limited in size, but not limited in scope. There are no walls, there are no edges, there is no middle. That's why the answer to where did the Big Bang happen is right here, also everywhere else. All of space and time were once packed into that unbelievably hot and thick state. It's not just an idea either. What has been seen supports it. We can see that the cosmic microwave background radiation is coming at us from all directions. You wouldn't think that if there was a center somewhere, all over the place. That sounds like the echo of a beginning. We're not off to the side. We are not in a neighborhood of space far from the action. We're also not the most important thing in the world, or at the center of everything. We are only a small part of a huge, growing whole. Nowhere is the heart, and everything is somewhere else. And that truth might be the most humble of all. The holographic principle. Visualize yourself holding a snow globe. Inside is a small world, maybe a winter town or a castle, surrounded by snowy wind. Imagine being told that everything that's going on inside that globe is written on the glass's surface in some way. Not just a picture, but the whole scene's physics down to the last speck of snow, wind gust, and second of time, written in 2 dimensions on the outside. That's the basic and mind-bending idea behind the holographic principle. It suggests that all the information about our 3-dimensional universe, including everything happening inside it, may actually be described by information encoded on a distant 2-dimensional boundary, a kind of cosmic screen. Like a hologram, the 3D world we experience might be a projection of a deeper, lower-dimensional reality. To understand why physicists even entertain such a wild idea, we need to begin with black holes. In the 1970s, physicists like Jacob Bekenstein and Stephen Hawking began exploring the thermodynamics of black holes. They discovered something astonishing. The amount of information, or entropy, that can be stored in a black hole is proportional to the surface area of its event horizon, not its volume. This was strange. In most physical systems, entropy, a measure of disorder or the number of microscopic configurations, scales with volume. A room filled with gas molecules, for example, has entropy that depends on the space the gas occupies. But black holes don't work like that. The amount of stuff a black hole can hold seems to depend on its skin rather than its insides. One bit of data spread out over a Planck area, which is the tiniest possible area of space, equal to about 10 min. This made many think of a strange but strong idea. Maybe black holes are just the start. This could be how the whole world works. This brings us to the holographic principle, first proposed in the 1990s by Gerard 't Hooft and later expanded by Leonard Susskind. It proposes that all the information contained in a volume of space, even our entire observable universe, might be encoded on its boundary surface. It's a radical departure from how we normally think about reality. But in 1997, it gained serious traction through a breakthrough called the ADS-ECFT correspondence, a mathematical duality discovered by theoretical physicist Juan Maldacena. In short, there is a mathematically identical description that lives completely on the border of a certain type of space-time, called anti-de Sitter space, AD-S. It is called a conformal field theory, CFT. Equations on the outside can explain everything that is going on inside the room. These two hologram states are very useful in string theory and quantum gravity. One world with gravity and one world without gravity can be two sides of the same coin, even though they look very different. Our universe is not a G-space. Instead, it is flat or slightly positively curved spacetime. However, the similarities point to a deeper idea. Perhaps our universe is also an image. If it's true, it would change everything about how we see ourselves. Think about this. What if the very edge of the universe holds information about every planet, star, particle, and moment in time? It could even be on the cosmic horizon, which is the farthest distance light has had time to reach us since the Big Bang. That edge, which is 46 billion light-years away in all directions, could serve as a screen, a flat surface that stores the quantum information of everything inside it. And we, living our three-dimensional lives, are simply experiencing the projection of this information as physical reality. But how can this be? How can we be shadows of something more fundamental? We'll look at holograms again to help you understand. You can find these on credit cards and unusual things. When lit properly, a flat surface with tiny interference patterns can make it look like it has depth in 3 dimensions. There is a lot of information on the surface, but the experience feels like it has depth. When you look at the holographic principle, this comparison is taken to its logical conclusion. It's not just an illusion of depth. Everything in reality, from quarks to awareness, comes from a deeper 2D layer that we can't see. Of course, this is still just a lot of theory. We still don't know if the world really works like a hologram, but there are some enticing hints. For instance, the entropy bounds derived from holographic arguments match those found in cosmological models. Attempts to unify quantum mechanics with general relativity, especially in quantum gravity research, find common ground in holographic approaches. And in some models of the early universe, the inflationary period might have imprinted holographic information on the cosmic microwave background, subtle signals that astronomers could one day detect. It also has very important philosophical consequences. What does it mean to be in a certain place if the world is a hologram? Does space itself appear, meaning it's not a real thing, but a useful illusion? Is gravity really just the sound of more complex quantum reactions happening on a flat surface somewhere outside of our perception of reality? Also, this is very strange. If reality is stored on a surface, what's below that surface? What does the holographic principle have to do with our search for the edge of the universe? There might not be a wall in space. If there is a limit, there might be a limit in knowledge, a spot where the information about our world is kept, like the edge of a hard drive where the program is kept. This edge might not be in space at all though. It could be math, in code, in the reasoning of pure quantum. So the holographic principle doesn't just point to what's outside of space and time. It changes the whole question. The edge might be the code itself. What happens when that code runs is what we see, hear, feel, understand, and even think. Still, we don't know. But by thinking about it, we are already pushing the edges of what is real. Brain cosmology. What if the world we live in is only a small part of a much bigger, more complex one? This is the main idea behind brain cosmology, a theory based on string theory that says the universe is made up of a 3-dimensional fabric, or brain, that is surrounded by a higher dimensional area. The word brain comes from the word membrane, but you wouldn't find it in a biology book. It's a theory that could completely change the way we think about life. In our everyday experience, we live in 3 spatial dimensions: up, down, left, right, forward, backward, and one of time. But string theory, the mathematical framework that attempts to unify all the forces of nature, proposes that more dimensions might exist. In some versions, there are 10 or even 11 dimensions. Most of them are compactified, curled up tightly on scales too small to detect, but a few might be extended in ways that allow entire universes like ours to exist as 3D brains floating inside a higher dimensional space called the bulk. In this scenario, we're confined to our brain. Everything we know, atoms, light, gravity, mostly planets, and even ourselves, is stuck on this 3D surface. The particles and forces of the standard model of physics are localized to the brain, meaning they can't move into the higher dimensions, but the bulk, the multi-dimensional space in which brains reside, could contain other brains, other universes, and maybe even entirely different laws of physics. Amazing things happen. As a result, one of the most interesting things about brain theory is that it suggests there might be other brains moving around in the mass, with higher dimensions. These brains might be other worlds, each with its own galaxies, matter, time, and maybe even different kinds of life that are controlled by different laws of physics. Gravity is one of the few forces that can leak into the mass. So even though we can't directly affect these brains, we might still feel their pull. This idea helps to solve a puzzle that has been around for a long time. Why is gravity so much weaker than the other basic forces? If gravity can spread into extra dimensions, but not other forces, then the gravity we feel on our brain is weaker than it is elsewhere. This leakiness might be a sign that experiences on higher levels are not only possible, but required. One theory, called the ekpyrotic universe, says that the Big Bang wasn't the start of space and time, but rather the result of two brains colliding with each other. They released a huge amount of energy when they hit each other in the bulk of higher dimension. It was enough to start the fast growth of our universe. From one point of view, this brain crash would have caused what we now call the Big Bang. From another, it was a cosmic rebound, a part of an endless series of collisions and growth. Imagine two huge unseen sheets moving through an ocean of other dimensions. When they hit, boom, there is a birth. Then they move back together, and the process starts all over again. From this point of view, the universe is not a single event, but a process that goes around and has no real beginning or end. What else is there besides our world? In this model, there could be a whole family of universes, or other brains, with their own laws and developing in their own way. Some might be completely alien, full of strange matter, and shapes that you can't even imagine. Some others may look exactly like ours. There are also some that may be only microns away from us, which is smaller than your own heartbeat, but will never be reached by normal means. If another brain crashed into ours again, it might start a new Big Bang in space, which could restart or even destroy our universe. These aren't just ideas from science fiction, they're theoretically possible outcomes of string theory. It's hard to believe in brain cosmology because we can't see extra dimensions or other brains directly yet, but experts are looking for proof that can't be seen directly. As an example, it is possible for gravitational waves to carry echoes of how they interact with other brains. Small changes in the cosmic microwave background could be signs of brain crashes that have happened in the past. Particle accelerator studies, like the ones at CERN, might find proof of extra dimensions or particles escaping into the mass. What does it say about the universe's edge? The idea of an edge is changed in brain cosmology. There is no wall or black hole at the end of our world. Instead, it's like a sheet floating in a deeper reality, with no edges in our own. If you kept going in the same direction, you would always be on the brain. If it loops back on itself, you might go around it, but you would never leave it. You would have to go into a whole different plane to go beyond, which may not be possible for beings like us, unless, and this is a very big if, there are quantum tubes or holes in space-time where the brains touch. For now, these are just guesses, but the idea is interesting for both science fiction and theory talks. In what part of the universe does the fabric of our universe thin out? Could we see or even touch another world? There, bubble universes. What if our universe is just one bubble in a big ocean of space? What if there are a million more popping up all the time? This is the amazing idea behind bubble universes, which comes from the theory of endless inflation. It changes how we think about what might be out there beyond what we can see in the universe. It would mean that our universe is not the only one out there, and that the huge reality we experience is just a small part of a multiverse that is so much bigger than we can imagine. First, let's talk about cosmic inflation, which was a very short but very explosive event that happened a very small part of a second after the Big Bang. The idea of inflation says that space didn't just get bigger, it grew bigger faster than the speed of light. This smoothed out any bumps in the space-time and explains why the universe looks so uniform now. A lot of people agree with this idea, and studies of the cosmic microwave background greatly support it. But some ideas about inflation, especially those that come from quantum field theory, say it never really stopped. Instead, endless inflation says that inflation stopped in some places, but is still going on in others. These quieter areas, where inflation stops, make bubble universes, which are separate areas of space where the fast expansion slows down and makes room for galaxies, matter, and life. It's like a bubble around us, but there could be a huge number more. Physics rules could be different in each bubble world. There could be different particles, forces, and even dimensions. In some, the pull of gravity might be higher. Stars might not form, or atoms might not stick together. Conditions in some places might be even better for living things than here. And what's even stranger is that they might always be out of reach, growing farther away than light and losing their edges as quickly as they appear. So how do these bubbles form? The mechanism comes from the quantum fluctuations of a hypothetical field called the inflaton field, which drives inflation. Think of the inflaton field like a sea of energy. Occasionally, a fluctuation occurs that's strong enough to knock a region of space into a lower energy state. This transition causes inflation to stop locally, forming a bubble. Meanwhile, the rest of the field continues inflating, producing more and more bubbles over time. The process is self-replicating, like cosmic popcorn popping eternally. This gives rise to the multiverse, not in the science fiction sense of parallel timelines, but in the physical sense of a landscape of bubble universes, each with its own version of reality. But will we ever be able to see these other worlds? This is where things get tricky. Space is expanding faster and faster, so other bubbles are usually far away from us, divided by large areas of space that are still expanding. They are moving away faster than light can travel because of inflation, so we can't see them directly. However, some scientists think that if two bubbles came together and hit each other, it might leave a tiny circular mark on the cosmic microwave background, like a stone hitting water and making a splash. As of now, no such clear trace has been found. Some strange things, like the enigmatic cold spot in the CMB, have led people to think that they might be the marks left by bubbles crashing into each other in the past. Bubble worlds have philosophical and even spiritual effects that go beyond the realm of science. In a multiverse that goes on forever, every option takes place somewhere in a different world. Earth might have formed in a different path, and dinosaurs might not have died out. One where the laws of nature are just a hair different, which is small enough to stop all life, and another where advanced civilizations thrived a very long time before ours. There may even be copies of you living in boxes that are similar to yours, but a little different from them because they were made by rolling different quantum dice. Some physicists agree with this thought and say that the multiverse is the reason why our world seems to be so good for life, stars and planets. No, the world wasn't made just for us. We just live in a bubble where things are perfect, because no one else could survive in the billions of places where they aren't. But some people fight back. They say that the multiverse might not be able to be proven wrong because it can't be tested, which means it's not part of standard science. Can the idea ever be proven? If we can never see another bubble, proof is still being gathered in a roundabout way. Eternal inflation comes from known science. It doesn't need any strange theories, and if other expectations of inflation line up with what we see, like how the CMB is structured, it gives the overall framework more weight. It's even been said that the flatness and uniformity of our world are best described by the idea that it's just one bubble among many. What does this mean for the edge of the universe? The edge in the bubble universe model is not a spot in space, but the edge of inflation. Our universe came from a bubble where inflation stopped, surrounded by a storm of space that was always expanding. It would be like trying to reach the edge while swimming uphill in a river that moves faster as you go. You can't get there, and the water never stops moving. But in theory, if a way were found to punch through the inflating barrier, a kind of quantum tunneling into another bubble, we might experience a universe with utterly foreign laws. Most likely, such a journey would be instantly fatal, as the energies involved would tear apart any familiar matter. But the idea remains one of the boldest frontiers in cosmology. The equiprotic universe. Think about the universe as a whole, with galaxies, stars, planets, and everything else, not coming into being in a fiery explosion from a single point, but through a clash of galaxies, a planned, slow but unbelievably strong crash between two huge S+ sheets. This is the idea behind the equiprotic universe, which is a very different explanation from the usual Big Bang one. The term equiprotic comes from the ancient Greek word ekpyrosis, meaning conflagration or out of fire. It refers to a recurring cosmic event described by the Stoic philosophers, where the universe cyclically burns and is reborn. In modern cosmology, the term has been repurposed to describe a theory rooted in string theory and higher dimensional physics, one where our universe is not the product of a single point of origin, but of the clash between two four-dimensional branes. Brane cosmology, which is an extension of string theory, says that the universe might be a three-dimensional brane, short for membrane, floating in a four-dimensional area, known as the bulk. Imagine our world as a huge dark sheet of space that is stretched out in a cosmic dimension, with other sheets of space. In the equiprotic model, there is at least one other brane that runs parallel to ours, and is split from it by an extra spatial dimension. This extra dimension is so small that we can't even see it, but it's there. It's possible that this other brane has its own world, physics rules, and kind of space and time. After that, it moves. The two branes move toward each other over very long periods of time due to gravity, pull, or quantum effects. When they hit each other, the kinetic energy is turned into matter and radiation, which is what we think of as the Big Bang. The catch is that this model doesn't start with a singularity. There is no point with an infinitely small density. The Big Bang is now just a transition, a time of extreme energy release, caused by a brane collision. The universe doesn't just appear out of thin air. It grows from a structure that was already there and has been getting ready for its next move. The branes bounce apart after the crash. As in normal astronomy, the energy fades away, space grows, and galaxies form. But in the end, the branes slow down, turn around, and start to move back toward each other. This leads to another crash, a new world, and the Big Bang. This will never end. This is the cyclic form of the equiprotic model, which says that the world is born only once and then born again and again. Each cycle could last up to a quadrillion years. After each bang, everything starts over with new physics, new stars, and maybe even new kinds of life. The universe stops being a straight line of events and starts to have a moving, living being. One of the strongest motivations for the equiprotic model is that it provides solutions to deep cosmological puzzles. The flatness problem. Why is the geometry of space so close to perfectly flat? The horizon problem. Why does the universe appear so uniform, even in regions that seemingly couldn't have communicated with each other? The singularity problem. How can physics explain a beginning from nothing if singularities break all known laws? One way that eternal inflation solves these questions is by positing an exponential growth that evens things out. However, the equiprotic model suggests a different way. It says that the slow, ordered contraction that happens before a brane crash can make conditions that are smooth, flat, and uniform, which naturally lead to our universe. There is no need for an inflationary blast. It gets even more exciting with physics. This model includes 11-dimensional space, quantum fields, and the behavior of branes, because it is connected to M theory, which is one of the best ways to bring together quantum physics and general relativity. This theory says that each brane is like a blank surface that a universe can paint on its own. There is energy and fields in the area between branes, which can change the result of each new cosmic cycle. Now, what would it mean to exist between brane collisions? From a physical standpoint, we might experience little difference. Life on Earth, galaxies, cosmic structures, they form and evolve just like in standard cosmology. But over immense time, the universe would begin to stop expanding, and contract ever so gently. The stars would die out, space would become cold and dark, and then deep in this dark epoch, the branes would once again come together. Bang! A new universe, fresh and hot and teeming with possibilities. For me, the most interesting thing about the equiprotic model is that it makes statements that are different from inflation. For instance, it says that the gravity wave background which is the deep hum of the early universe, should be a lot less loud than inflation says it should be. It also shows small trends in the changes in the temperature of the cosmic microwave background, CMB, which might make it different from other models. These ideas might be proven or disproved by future tests, like ones that measure the CMB or gravitational waves with more accuracy. Many old beliefs, from Hinduism's breathing Brahman to the Stoics' idea of endless return, are deeply connected to the idea that the world is eternal, cyclical, and renewing. It changes how we think about cosmic death, not as an end, but as a disguised beginning. From this point of view, the edge of the world is neither a physical limit nor the end of time. It's the line between cycles, the line between times. If you could stand on the edge of two brain collisions, you would be in the middle of two different times and see one world end and the other begin. Quantum tunneling into new realms. Imagine that you are standing on the edge of everything, time, space, and energy, and then, all of a sudden, you feel like you are not there. It was not erased or destroyed, but written over, not ending, but starting somewhere else. This is the reality that quantum tunneling on a cosmic scale describes. It's a strange and confusing event that lets particles cross barriers they shouldn't be able to, going against classical laws as if they were led by secret odds. Use that for the whole universe now. When it comes to the quantum level, particles don't act like balls on a table. They don't have a clear place because they live in a fog of options. Particles can sometimes appear on the other side of an energy barrier when everything else seems to say impossible. This is called quantum tunneling. It's how the sun burns, how radioactive matter breaks down, and how life itself moves forward, one very unlikely atomic leap at a time. Now, scale that up. What if the universe itself could tunnel, not through space, but through states of reality? Some physicists believe that what we perceive as our universe, with its familiar laws of physics, constants, particles, and forces, is just one configuration in a vast landscape of possible universes. In string theory, this is referred to as the string landscape, a nearly infinite array of vacuum states, each with its own set of physical laws. Our universe, then, is like a marble resting in one valley among many peaks and troughs. According to quantum field theory, the vacuum isn't truly empty. It's a seething, fluctuating sea of energy and potential. And in this sea, it's possible for a region of space to suddenly tunnel from one vacuum state to another, from a false vacuum, a local minimum, to a true vacuum, a lower energy state. It's the cosmic equivalent of the ground beneath our feet suddenly giving way, not into a hole, but into another kind of existence entirely. This event is called vacuum decay, and while it sounds apocalyptic, it's fundamentally a shift in the fabric of the universe itself. The bubble of true vacuum would expand at the speed of light, replacing the old vacuum and everything within it with a new one. The laws of physics, the constants of nature, even the number of dimensions could change. Space and time might reconfigure, matter could be erased or reshaped. If quantum tunneling between vacuum states is real, then the idea of the universe's edge is more like a covering between different worlds. We could be just one bubble in a huge froth of worlds, each one born from a quantum fluctuation and separated by lines we can never cross unless the universe changes the rules. This means a lot of things. It means, among other things, that the world is metastable. There isn't a very low energy level, but it's stable enough for now. But quantum physics says that tunneling could happen if there is enough time. This is not science fiction. It's a real projection based on what we know about astronomy and field theory right now, based on the Higgs field and the known masses of fundamental particles. Some scientists even think we can guess how likely it is that such an event will happen. If a vacuum decay occurred, the bubble of new reality would expand at light speed. There would be no warning, no time to observe, no time to react. It would be, in every meaningful sense, instantaneous. But rather than being a cold end, it might be the beginning of something else. Inside the bubble, a new universe could emerge, one with different laws, different constants, maybe even different forms of matter or life. So, what lies outside the edge of the universe? Maybe it's not just space, maybe it's probability, a rolling dice of quantum outcomes, where entire universes shift, blink, and shimmer into being. Maybe we live on a ledge of potential, perched between one vacuum and another, oblivious to the invisible thresholds all around us. This makes me think of a multiverse that is both scary and beautiful. It's not made up of different spaces, but of options that are close together, like musical notes ready to be played. If quantum tunneling is real in the universe, then the edge of the universe isn't a wall or a blank. It's a way to get to other worlds, not traveled with ships or probes, but with time and chance. Even more interesting, some ideas say that tunneling might not only fill in empty space, but it could also make new bubbles. This is like the idea behind endless inflation, which says that every tunneling event creates a new world. Each bubble grows and changes on its own. This is the bubble we live in. There could be a huge number more, split not by space, but by energy state and cause and effect. What if our own universe was born this way? In this view, the Big Bang wasn't the beginning of everything, but merely the birth of our particular vacuum bubble, emerging from a parent state through quantum tunneling. We didn't arise from nothing but from a higher energy realm that spilled into being, cooled, and formed everything we see. And what about the edges of this bubble? They're unreachable. They expand at light speed, just like the outer limits of our observable universe. But unlike the edge of a balloon that we could someday catch up with, these edges aren't physical locations. They're the transition zone between two distinct realities. The outside is not space we can reach, but a different physics altogether. But it does bring up an interesting question. Could we ever pick up the weak sound of tunneling? Could we see the mark of a vacuum bubble crashing into another? It could be in the form of faint scars on the cosmic microwave background, or strange changes in energy and shape. There are experts who think it's possible. They have been looking for clues, like hints of curves, cold spots that can't be explained, and sudden changes in temperature or density. The door is still open, even though nothing solid has been found yet. Some of the most important things in the world stay hidden until we're ready to ask the right question. And even if we never see the tunneling happen, its implications linger. They whisper of a cosmos in flux, a reality where what exists is only temporary, a fleeting chapter in a much larger book. Quantum tunneling isn't just a quirk of particles. It may be the engine of cosmic renewal, the spark that lights new realms when old ones fall away. Dark flow. Even though it's not something we can see or touch with our tools, there is something out there that pulls on our universe like a secret current under a huge ocean. This unseen force is called dark flow, and its presence is still hotly debated. However, it is one of the most tantalizing signs that there might be something bigger, stranger, and completely unexpected beyond what we can see. The story begins with the cosmic microwave background, CMB, cold spot and bubble worlds in the multiverse. According to current structure formation models, the cold spot went from being a normal, if rare, event to a cosmic puzzle. A theory that is gaining attention suggests that the cold spot might be a scar from a clash between bubble worlds in a multiverse. Some models of inflation propose that our universe is just one bubble in a foam of space that is always expanding. These bubbles might occasionally collide, much like soap bubbles in a sink. If such an event happened very early in the universe's history, the impact could have left a mark on the cosmic microwave background, CMB, either by altering its temperature or shape. The cold spot could be such an imprint, a ghost of another world that briefly crossed paths with ours before drifting away, never truly gone. This other universe, with potentially different physical rules, may have touched ours at some distant point in the past. However, it lies beyond our causal reach, meaning we wouldn't be able to observe it directly. Yet, we might detect its aftershock in the CMB, a small region of cold, an anomaly in the grand scheme of things. This theory aligns with concepts like eternal inflation, suggesting that space continues to expand forever in some regions, while pocket universes occasionally form and solidify. Each of these pocket universes could have different physical constants, with some not supporting life as we know it. From this perspective, the cold spot is not merely a random temperature fluctuation. It may be a message from beyond the stars, inscribed in the light from the Big Bang. Yet the cold spot remains controversial, with some scientists cautioning against jumping to exotic conclusions. The universe is vast, and rare phenomena can occur in large datasets. Even if the probability of such a cold region is low, it might just be cosmic variance, a statistical fluke. Could there be other, subtler anomalies in the CMB? Hints pointing to new physics. Some researchers are using machine learning to search for patterns in the background noise, looking for signs of bubble collisions or topological defects. Others are scanning for non-Gaussianities, deviations from the expected statistical distribution, which might signal new physics. Unobservable galaxies. We can observe hundreds of billions of galaxies, each containing billions of stars. However, what we see is only a tiny fraction of what exists. Beyond the observable universe, there are galaxies we will never see. This is due to the fundamental limitation that light has a speed limit, and the universe has an age. The galaxies beyond our cosmic horizon exist, but the space between us and them is expanding faster than light can travel, meaning their light will never reach us. These galaxies are as real as the Milky Way, with stars like our Sun, and possibly even intelligent life. But because of the expanding universe, they have slipped out of our reach. The Hubble Space Telescope and James Webb Space Telescope, JWST, have given us glimpses of the vastness of the observable universe, revealing around 2 trillion galaxies. However, this is just the visible slice. The unobservable universe could be vastly larger, hundreds or even thousands of times the size of the observable universe. In these hidden realms, the rules of physics could differ, leading to galaxies where the stars are made of strange particles or gravity behaves differently. Some places might not even be suitable for life as we know it, but there may also be galaxies remarkably like our own, with spiral arms, supernovae, planetary systems, and perhaps civilizations. The edge of the universe and the limits of light. Light is our window to the universe, but it has its limits. The cosmic microwave background, CMB, is the oldest light we can observe, coming from around 380,000 years after the Big Bang, when the universe had cooled enough for photons to travel freely through space. Before that, the universe was opaque, and light was constantly scattered. This makes the CMB the ultimate limit of electromagnetic visibility. We can never see light from before the CMB, as no photons from that time were free to travel. The cosmic dark ages followed the CMB, a period before the formation of stars and galaxies, when the universe was cold and dark. Eventually, the first stars and galaxies began to form, ending the dark ages. Yet even with advanced instruments like the JWST, we can never see beyond the CMB or into the pre-stellar darkness. To explore even further back, we would need to use non-electromagnetic messengers like gravitational waves or cosmic neutrinos. Gravitational waves are distortions in space-time caused by massive objects like black holes merging, and they can pass through the early universe where light could not. However, these waves are weak and difficult to detect. The cosmic neutrino background, which dates back to just seconds after the Big Bang, is another potential way to peer into the universe's early moments. The anti-universe theory. Some cosmologists speculate that the Big Bang wasn't the start of time, but rather a point of change, dividing 2 realms, our universe, which moves forward in time, and a mirror universe, the anti-universe, which grows backward in time. This anti-universe would consist of antimatter and would experience all physical processes in reverse. This idea of an anti-universe could also help explain why our universe contains far more matter than antimatter, an unsolved puzzle in physics. If the anti-universe theory is correct, the antimatter from the Big Bang didn't vanish, it just exists in the anti-universe. Some researchers believe that neutrinos, ghostly particles that barely interact with matter, could be a sign of the anti-universe. In this case, right-handed neutrinos, which we've never observed, might be from the anti-universe. Gravitational waves. Gravitational waves are ripples in space-time caused by massive objects, such as black holes merging. These waves were first detected in 2015, confirming Einstein's century-old prediction. Gravitational waves can provide insights into the most violent and energetic processes in the universe, offering a new way to observe the cosmos. In conclusion, the mysteries of the universe, from the enigmatic cold spot in the cosmic microwave background, CMB, to the unobservable galaxies beyond our reach, challenge our understanding of the cosmos. Theories, such as bubble collisions in a multiverse, the potential existence of an anti-universe, and the limitations of light itself, push the boundaries of physics, suggesting that what we observe may be only a small fraction of a much larger, more complex reality. Gravitational waves and other non-electromagnetic signals offer exciting new avenues for exploration, potentially unlocking deeper insights into the universe's origin and evolution. While many questions remain unanswered, these cosmic puzzles invite us to continuously expand our thinking, blending science with philosophical contemplation as we seek to understand the vast, mysterious universe that surrounds us.